that I'm going to talk for shorter time. To talk too much about nuclear astrophysics because I guess you all know more or less what is the business, but probably you are not very much. At least some people don't know very well what is the difference between direct and indirect techniques. So usually when we make an experiment, you have just few ingredients. Okay, you have the beam, you have the target, and you have the detectors. So it seems everything is easy, but in reality, it's not that easy because you have so many technical problems, let's say, that makes the situation much more complicated. One of the most crucial points is that you go for nuclear astrophysics, you have to go to very low energies because stars are cold for nuclear physicists. And so the cross section is very small because of the Coulomb barrier. But this is not only the only problem. You have vanishingly small signal to noise ratio. You have the electron screening that is preventing the access of the low energy region. And this is a typical sketch. So in any case, you need to make some extrapolation. That's the most point, at least in most of the cases. And that is the situation today. Maybe in the future, there will be available new techniques that will allow you, for instance, I don't know, storage rings where you can have ions that are fully stripped, things like that. So probably also the probable electroscreen will be solved and you can make the measurements directly down to low energies. But so far, one of the best techniques that we can use to get to astrophysical energies without extrapolation is using indirect techniques.
Sorry, there is a message here, warning message.
I think you have to go to the laptop. No, go to the laptop with the mouse. With the mouse, you click on OK.
It's on the TV. The laptop. You just need to get the TV remote.
No, she has to press OK.
No, it's on the TV. It's the TV, not the
Yeah, okay. TV got tired. It's so we spare energy, you know. We are like green people, environmentalists.
Just turn the TV on.
Turn the TV on.
And put the TV the football match. Yeah. This is bottom boring. No, still you see. Anyway, so you have to add an additional ingredient that is nuclear reaction theory most of the time, because instead of measuring the reaction you need for astrophysics, you are going to measure another process. And so in order to link the two reactions, the two cross sections, you need to have some nuclear reaction model. Of course, this is helping you in some sense that you don't need to measure very low cross section. You have like usually very clean and very high signal to noise ratio, very clean channel selection. But the other problem is that you have additional different systematic errors coming, for instance, from the model that you have to use to link the two cross sections. So this briefly is like the difference between the two approaches. The good point is that you can always attempt the measurement in the two-way and check for consistency. That would be like a very interesting thing. And this is something that has been reached many times. One example is the carbon-13 alpha N, for instance, for which we got very good agreement between direct and indirect measurements. Okay, let's go a little bit about one of these indirect methods. Of course, there is a lot of them. You can make, there is, for instance, the ANC that you have probably heard about. There is based on transfer reactions. There is you can measure the spectroscopic factors. You can use the inverse reaction. So there is plenty of methods, and one of the approaches is this Trojan horse method. There are several kinds. I mean, this has been developed through many over the years using many different approaches. So, for instance, here it's what you can see. In the case you have resonant reactions, but thanks, for instance, to the work of Agram Gamezanov, Stefan Tiepel, we have different approaches depending on the reaction. So we have more refined models than the usual ones. So the basic, it's shown in this picture for an example that I'll show you later on. That is the aluminum 27P reaction. So the basic idea is that you have this deuteron and you well, fire deuteron, in this case was aluminum, not a deuteron target, and then you transfer a proton. Since proton neutron have just nuclear interaction, if you have these two particles, proton neutron, very far away, then you have no interaction between the two. How do you impose that these two particles are far away? You do by selecting a very small momenta, relative momenta between the two, because small momenta, relative momenta means that the distance is very big. In this case, these two particles are independent. You have this what we call quasi-free process. Okay, when you have essential interaction of only one particle. This way, you can populate, in this particular case, resonances in aluminum 27 plus proton, so in silicon 28. And you can get the resonance strength from this. This is just like one of the approaches. This is like parallel to what you can do with the NC. In this case, you have a transfer to an unbound state. Usually, when you measure NC, you have and you perform a transfer to a bound state. So this is very linked between the two. And in fact, over the years, we have shown a connection, and it's also very good because you can check the agreement between the different indirect methods. Going more into the details, this is the typical equation that you find in any paper from our group, and it's the very simple, the simplest formula you get for this method. Okay, so we measure the one with the red balloon. It's this triple differential cross-section, the cross-section of this reaction with three particles in the exit channel. If you do the math, you get a quite simple formula under some assumption. Assumption are, for instance, that you have plane waves. There is one of the approximations. That you are under quasi-free conditions, as I said before. So you get essentially two factors. One factor that is easy to calculate, that is the one in the green circle, and another term that we call half of energy shell to body cross-section. That is the cross-section of the reaction, for instance, aluminum 27p alpha. Why we say that this is half of energy shell? Because if you go back to this picture, you see that the particles like magnesium 24, helium 4, these are real particles. You measure it, okay? On the other hand, and these are the ones on the exit channel. So these are real because you measure it. But the problem is like coming from a transfer. So this particle is not real. You don't observe it. It's like when you have like virtual photon exchange. So this is a virtual particle. So it's not on the energy shell. So that's why we say half of energy shell, because in the exit channel, we are on the energy shell, but in the entrance channel, we are not. And these have implications. Good implications, I would say, and bad ones. First of all, okay. The good one, as I will show you better in the next slides, is that you are free from Coulomb suppression. And this is something we like, because this makes it possible to go to astrophysical energies. On the other hand, this means that you are not measuring, of course, the cross-section of astrophysical interest. You are measuring something else. And you need to take into account this factor. Okay, so now I go to the scary stuff. It looks scary, but in reality, the ingredients are quite. I usually show this because some people say, "Oh, but that equation is very simple. Look, how can you get anything out of this?" But in reality, we have also complicated equations for people like the business, and but still, this if you focus on some stuff, it's not so complicated to understand. And in reality, this is very similar to what I've shown you before. First of all, this is the amplitude that we know. This is the one that we need. This is what we call the momentum distribution, okay? And this is the stuff that was in the green circle in the previous slide, okay? So still we have, of course, this is the amplitude, is not the cross-section, so it's the square root, let's say. So you have a dependence on the relative momentum between the two particles X and S that were like proton and neutron in the previous slide, okay? Then you have some angular dependence, so the effect of spin and so on, that you remember that were not present before because it was a simplified equation. You have other phase shift, but here it comes very interesting point, okay? In this equation, you guess the inverse penetration factor in the entrance channel. So it means that when you write all this stuff here, essentially you get automatically from in your cross section that you measured a correction factor that let's say eliminates the penetration factor in the entrance channel. Okay, so that's why we can go to astrophysical energies without suppression, because if you do the math, you get this penetration factor to -1 that is compensating the one that is entering your cross sections. Okay, so that's why it's good. This is a good point. Apart from all these sums and indexes and so on and so on. This is a very crucial point. It's telling you that we can go to astrophysical energies without extrapolation. Then this is like the core, like the cross section. So you have this. In this case, we have, like you said, an arithmetics-like approach. Okay, so essentially we are writing the cross section as a sum of resonances, some Bertigna, let's say, and the resonance parameters are hidden inside this A matrix. Okay, so this is essentially your cross section. Of course, with this p to -1/2 because it's square root, that is compensating for what is happening inside this A matrix. That is the effect of the cross section. And you have, as this is arithmetics, like boundary conditions and some correction for alpha shell effects that are usually quite small indeed. But you can do, if you like, you can do the math to check it. Okay, so that's more or less the complicated part of the story. Okay, so it's a kind of a proof that when this equation is apart from the many factors justifying what we do usually with the previous equation, it is like the simple one. Of course, I was telling you mainly, I was talking about the easy case. That is the one when you have a proton and neutron in the exit channel. Okay, that is the simplest case, because of course you have the neutron that is a proton and neutron that loosely bound. So it's the ideal, what we call Trojan horse nucleus. That is the system that you use to transfer the reaction, the particle that we need to induce the reaction. But in reality, you can have also charged charged spectator, we call. Okay, so like in the previous case was neutron, that is the particle that is not taking part into the reaction. So if it is charged, what do? You have to do some Coulomb corrections. Okay, and this is one of the formulas that you can find in the literature about this Coulomb correction that is in this paper. Again, it's Agram work. It's done a lot of work, as you know, about the Trojan horse method, especially in the case of resonant reactions. This zeta here is coming from the Sommerfeld parameters. It's a combination of the Sommerfeld parameters. And the good point also in this case is that under some conditions, this renormalization factor is almost 0. Okay, so it's essentially like not introducing a big correction to this term. So it's like all this stuff that is in the red circle gets down to 1. Okay, of course you have to check, you have to make sure that all this stuff is working, but this just tell you that you can have the systematic errors, but if you do all the math, you can check that all these systematic effects are under control, or more or less what is the uncertainty, the model uncertainty that you introduce. Okay, so let's compare what we get with what we would like to get. That is the comparison. This is a simple case where you have like 2 resonances. You see, in this case, I'm summing over 1 from 1 to 2. You have just 2 resonances. And this is the difference between typical aromatic expansion for your cross-section for the astrophysical factor, indeed, in the case of the direct reaction and in the case of the HM approach. The core is this D matrix. Okay, this is containing all the reduced gamma widths. And this is telling you that the shape is almost the same. What is different is essentially 2 points. The first one is that you have to multiply by the penetration factor that is hidden inside the gamma, okay, because gamma is containing the penetration factor. And the second point is that you need normalization, okay, because instead of having, as I've shown you before, instead of having the gamma for the entrance channel, okay, of course you don't have, because otherwise you have the penetration factor there. You don't have. You have this p to -1. Instead of this, you have these transfer terms, okay, to the resonances. Of course, you can calculate this ratio. You can fit it. That is what you usually do. Okay, we get some arbitrary normalization constant that we use to normalize our data. But in some cases, we could, because it's available in the literature, you could even take the ratio of this transfer cross-section and put there, and it's working. We have tested, for instance, in the nitrogen 15 P-alpha reaction that is working. So it's very similar with some constraints. And one of the main sources of uncertainty is usually this normalization constant that has to rely on existing direct data, okay, most of the times, because as I'm telling you, you can even use like data from the literature calculation, okay, of this transfer cross-section for the normalization. But usually, if you use these existing data for normalization, you can minimize because if you take from the data, you have the same uncertainty as your data where you make the normalization. The best thing is to have a very broad range where you can make the normalization, because you really reduce a lot or you normalize to more data sets in order to reduce the systematic error coming from the normalization. But in principle, you can do the calculation. But in this case, you add additional model dependence, okay? Because it's coming from the calculation, for instance, from the choice of the potential. So it's always something to pay, you know, whatever you choose to do. Okay, you get rid from the existing data, you get independent from them, but then you have to pay something because you have to have some model dependence in there. And this must be taken into account. Another interesting point is the possibility, that is very interesting, to go to negative energies. Okay, how do we get to negative energies? So if you write down the energy in your entrance channel for reaction of astrophysical interest, that is this AX, you can write as a function of the energy of the projectile, the moment of the spectator, and the bending energy. From this equation, you can get also negative energies for your EAX. So it means that you can span, and this is because this you have this off-energy shell particle in the entrance channel, so it's not the real particle. So you can get, let's say, to negative energy thanks to this. And you can choose all these parameters in order to go to negative energies. And so, like, you can explore the bound state region. Okay, so you get essentially NC for these cases. So it's showing a deep connection that you have between NC and THM. Okay, so this is very good because, for instance, sometimes you can choose to make like a comparison between direct data, indirect data taken with different indirect methods like NC and THM. So you can make really like, okay, you can try to have, let's say, overall agreement between different data sets thanks to this. Okay, it's very interesting when you have to reach some, okay, so if you have some cross-section, is very important, you have to reduce your systematic uncertainty. You can have this, let's say, broad check, trying to include everything, let's say. Okay, so now let's go to some experimental physics after so much questions. And I'll focus on 3 cases, okay? The aluminum 27 P-alpha reaction, where we use the deuteron. So this is, you know, the easy case, where you use deuteron for transferring your participant, that is the proton. Then I will talk a little bit about the carbon-carbon fusion, where I use a nitrogen 14 to transfer a carbon. So this is already very exciting. And the next case that we'll discuss, it's a very, you know, reaction that we are starting to study right now. We have so many troubles for this investigation, because in this case, it was the first time we're using neon 20 for transfer an oxygen 16. So you see, we like to test a lot in our equations, you know, to check to what limit we can use them. And in the last case, we already found that they were not working, and we had to develop a totally new theory, thanks to Stefan Tippel, who supported us in this development. Okay, so let's start from the easy case. This is aluminum 27 P-alpha reaction. So Sarah just gave you some astrophysical background, so I will not talk about that because, again, this is not really much into my, you know, say, skills. just tell you that this aluminum 27 is interesting because it's entering many scenarios. So for instance, you can ask if the magnesium aluminum cycle is closed, or it's entering, for instance, the normalization aluminum 26. And in the last years, there was not really very much improvement in the measurements. So most of the data coming before the, let's say, are coming from the previous millennium, I would say. And there was instead a very nice development in the calculation, in the methods for calculating the reaction rate that is using like Monte Carlo. And this allowed to really to squeeze a lot the uncertainty, as you can see from the picture. Still, if you concentrate on the blue band, you still have like around almost an order of magnitude uncertainty, So it's still very much uncertain. So this was one of the test cases that we used for measuring. And this is just, sketch of the setup. One of the important points in our measurements is that usually you can keep the setup very simple. That is the picture you see on the left. You have the beam, it's hitting a target where you have CD2, and you have detectors. In this case, we even didn't need any DE, detector for particle identification, because the channel was very clean. Okay. So, and this measurement was the first one that was done after the lockdown. So you see this me with mask and gloves. Never mount the detector with gloves, okay? Because if you have tiny screws, and that's get, like you have a projectile hitting your detector. So it's not a nice experience. I can tell you, better not use gloves sometimes. Okay, so just to give you an idea of the kind of measurements that we need. So these plots, okay, just don't mind the one on the right, that is the worst one. What we have is that, for instance, the first one, you have this equation. So you start from energy conservation, and you make some assumption that you see in the bottom left, where you can call y the energy of the beam minus energy of the particles that you detect, and x it's the momentum of one of the particles divided by 2u is unit mass. If you do the math, you get that all your events should gather along this line if they, of course, obey this energy conservation law. That is the one that is for your reaction. Okay. So if they don't satisfy your energy conservation law, it means that you are not correctly identifying your channel. In this case, we get two straight lines, and A, it's equal 1 from, you can fit, okay, get 1. But you have two lines. Why? Because let's say you have this additional term, this Q, that is the Q value of the reaction, and you have one line for your ground state and the other one for the first excited state. Okay, so indeed, if you plot the Q value of your reaction, you get two peaks and nothing else. You see, it's very clean. Luckily, you cannot see the picture on the right. And you see just two peaks, very sharp, that are corresponding for the two channels. So this is like background free. So it's very essentially background free. In reality, there is like a few percent, like less than 1% background that you see from, this stuff that is getting to like these red points below the Q value minus 2. That is giving this little tail that you see on the far left. Okay. In this case, we consider a ground state. That is the one that is most populated. So in this case, we have a wonderful signal to noise ratio. So the experiment, it looks it's working very well. We have to check that you don't have spurious contributions as we seen before. So what you do is that you have to make sure that you have not these non-quasi-free processes, like population of some silicon 29 compound system. So what we can do to this check is making this plot of relative energies. If you have, for instance, resonances magnesium 25, you should have horizontal lines, and you don't see them. Or if you expect to have like helium-5 excited states, you should get horizontal lines in the picture on the right. And indeed, if you see around 1, you see some structure. And then there is this spot, this yellow spot over there, like, Jupiter, but that we don't know what this is, but luckily it's sitting outside the energy region of physical interest, so we didn't care very much. And the other point that you do for checking that you have this quasi-free condition is this what we call momentum distribution. This is very important because this is entering your equations, okay? You remember from that big formula that you had this term. So we usually measure this and we compare with the theoretical curve and we got very good agreement. So it means that our formula is working, okay? You can take the experimental value for your momentum distribution. So going to the results, the main achievement of this measurement was the possibility to observe this resonance at around 80 keV. This is sitting right at our excitation, right at the gamma window, the energy range of statistical interest. In this case, for instance, in the attempt to reducing the systematic uncertainty, we did a normalization to 2 resonances, sitting at quite a high energy where you don't have any electron screening. In this case, we got very good results. So we could set we could do the measurement of the strength of these and set lower upper limits for nearby resonances that are not plotted, but it's not compatible with our result. So we did the calculation of the reaction rate, and this is what Sarah was showing before. Okay, so I'm not going too much into details. And good point is that we were able to get this factor of 3 lower reaction rate at the temperatures of statistical interest. This is just a very nice result thanks to the measurement of this resonance. So let's go to the carbon-carbon fusion. Again, this is very important. It's a key reaction for nuclear astrophysics, as you know, and because it's really entering a lot of scenarios, like, for instance, superbursts, determination of MAP, so this mass above which you can have supernovae. So it's very important, let's say. And using the approach that I sketched, but in this case, using this nitrogen-14 transfer carbon, having a deuteron as a spectator, so it's charged spectator in this case, we were able to get this cross-section down to 1 MeV, also even lower energies. So you see a band, but this is experimental data, okay? Usually plot like a band because otherwise it's a bit a mess. There are so many points around. So you get a line, and it looks easier. And also in this case, we had to rely on a normalization to the existing data. Okay, so of course, you have some systematic uncertainty coming from the normalization that you use. And in this case, the normalization was done around 2.5 MeV because the data are, in the future will be more data available, and you will see the talk, next talk is showing more data. So we can improve our normalization and reduce the systematic uncertainty, of course. But this is like something that we cannot do anything with. So you see some theoretical curves, and the most interesting one is the one that's showing you hindrance, because this is something that has also been supposed when you have this fusion reaction. Is there hindrance or not? Now result, and you know very well the paper by Aurora, this is showing you a pattern of with many resonances. So it's very interesting because of this. Also, in this case, you can show you some some plot showing how clean is our result, how good is the signal-noise ratio, when essentially the noise is zero in these cases. So, like particle identification, for instance, in this case, we had the possibility to observe 2 channels, the ground state that is often you don't measure it because to clean up your data, you need to make coincidences with the gamma rays. So, but in our case, we could observe very well the ground state and the first excited state that is, I mean, part, of course, of the cross-section, but should be the most important part. This is the second assumption in this data. So we focus only on these 2 states, ground state and first excited state. And you see the sketch that has been used. This is, if you remember that formula about the Coulomb correction, this is one of the cases where this eta combines and give you a negligible eventual contribution, okay? So essentially, in this case, you can see that this effect coming from the Coulomb interaction that you have between the deuterium and carbon-12 is negligible, okay? So this is an important proof. So you calculate the reaction rate, and because of the, resonances, you get an enhancement of reaction rate. And this is showing you more or less what you expect for different astrophysical scenarios, okay? Okay, that's the easy part. Let's go to, The good point with these measurements, okay, is that triggered a lot of theory and measurements. So this is very good because it's stimulating discussions, okay, in the scientific community to get some more reliable results for astrophysics, okay. So at least you see, sometimes you have these arbitrary factors in that you add in the astrophysical calculation, but you know, at least from our business as nuclear physicists, we try to reduce the arbitrary. And there was a work by Akram Muhamedjanov who said that you have to introduce some corrections to our data. And this corrected data is shown as these red points. These have some problems, and our is writing a paper that is pointing out these critical points and doing this calculation in a more correct way, because we have to take note of these Coulomb corrections, and you need DWBA. But DWBA means that you have you have to do it properly, let's say. So in this case, for instance, you are making a transfer to the continuum. Okay, so this is not easy to calculate because you need to get numerical stability. And other problems, for instance, with the potential or with the number of nodes. Okay, so we are addressing these problems doing from scratch a new DWBA calculation just to show you this result. But it's interesting, and probably Aldo can comment later on. Apart from these corrections, there's a number of new theoretical works that came out. For instance, this one from Aldo and John Atowitz. This is showing you how the resonances can affect and getting more in agreement with our result. Okay, this is just a hint that there's something that most of the calculation is giving you just this flat trend, is not taking into account that these resonances. And this has been confirmed by other theoretical work. This is by this Japanese group, Taniguchi and Kimura, who have done this AMD calculation, molecular dynamics, essentially. And this is showing you on the upper right, a paper that is published, and on the bottom left, some calculations that were shown in these conferences that was in October this year, okay? So the pictures, this is like stolen from the talk, okay? So it's a bit grayish, but what is interesting, it's what is reported in their abstract. And they were essentially, through their calculation, even if you change the potential, you're getting from Skern to Gourmet potentials. It seems that these hindrance that I was showing you before, it seems it's not confirmed, but these more advanced theoretical calculations. Okay, so there is a growing, let's say, proof that this trend that is going to very small astrophysical factors probably is not confirmed. But you know, the good point in science that you can get more money saying, okay, the situation is critical, we need to make more measurements, and that's good. We can keep working. You know, otherwise, if you measure everything, then we are not funding you anymore. Okay. Another interesting result that has been published very recently, and this is the paper that you can check, is from a Brazilian group who was using potential model calculation to get the trend of the cross section. This is looks very nice because introducing the coupling to the inelastic state channel, you can get a very nice reproduction of the resonances, and you have this growing trend in the astrophysical factor. This is a star, so this is corrected for the this. I mean, just to take the gross of the contribution out. Okay, so it's again giving you some hint that maybe what we have been thinking before this Nature paper was not the. I mean, we need to work more on this. That's my point. So there is hint that in reality you have to take into account resonances. The contribution, it looks like it's not going down for as we have for the hindrance. So these are hints. We need to make our work. So let's see. So let's go to the last point. I hope I have still time. I can talk for hours, so I'm trying to speed up a little bit. And this is what was a very complicated business. So we did the two measurements to get the fusion cross section for oxygen plus oxygen. It seems that the measurement was too good because we could measure really many channels. So excited state, the P channel, the alpha channel. So it was very complicated measurement. with very complicated setup. So you see on the right more or less the situation for this. And again, you have some uncertainty when you make the extrapolation. You have to write on some models. Here, the advantage is that you don't expect resonances, at least from the literature, you don't see resonances. The high energy region where you see the error, that is covered by existing data. But if you go to other scenarios where you have lower temperatures, still you have to rely on extrapolation, and you see the scale log. So it can be anything when you go to low energies. So that's why we wanted to carry out the measurement. And the sketch in this case that you have is the one you see on the bottom right. So in this case, we have neon 20 projectile, because the idea was to transfer an oxygen 16 and there's an alpha particle spectator. Okay, so also in this case, you can have these Coulomb interactions. This is an important point. So we had to rely heavily on the help of Stefan Diepel, who did all the calculations and to understand this. But there is another point that had to be taken into account, is that neon 20 is the fog. So what I've shown you before, that is this bell-shaped momentum distribution, just forget about it. It's situation got really crazy, and for many years we could not understand what's going on. Okay, so we had to develop from scratch a new, let's say, approach to the version horse that can be used also when you have this deformed projectile. Okay, this deformed Trojan horse nucleus, and this was one of the cases. So it's very interesting because this is really testing the method, the domain where the method is working. Okay, so people usually complain, say, oh, every measurement you do, you get nice result and you publish it. Can it be true? Well, it's not really true, because sometimes the approach is working, sometimes it's not working, and you need to make extra work to make it working. This is a lot of work. Also the word work, repeated many times. Okay, so just go more into the details. So this is a sketch again of the spectral setup, the targets, blah, 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 what you see. These are typical divigation plot. In this case, we had high energy protons, as you can see. So we had the particles punching through, we had the stack of detectors. It was a bit painful. You can see the number of cables that you have in this scattering chamber. Any cable is a trouble, let's say. So, but indeed, in reality, showing you some preliminary result that we hope we are writing the paper, just to tell you the situation right now. So the first thing is your identification plot. You remember the one that I showed you for aluminum 27 p-alpha reaction. In this case, you see a lot of structures. So the ground state, the first excited state, this one, I think that was for the alpha channel. So this Q0, Q1, etc., correspond to excited state on, let's say, one of the particles. In this case, it was the silicon 28 that you populate. So you see, you have a very nice reproduction, but only the Q0, Q1 are well separated. Qt and Q4, they correspond to the second and third excited state of silicon 28. You see a single peak, and then the levels get so close that you cannot separate very well. You need a very better resolution in principle to get them. So the idea is so far, let's concentrate on the ground state, the first excited state, to make where we have this situation that is better under control. Okay. Statistics, as you can see, was not very good. Even if we repeated the experiment 2 times, the amount of data we could gather was not very, very good. And because of this, we could not extract the astrophysical factor eventually. That is the one that we want to observe. So what we did was to do a validity test to check if our equations were working, okay? And we found out that they were not working, and we had to use this different alternative approach that was developed by Stefan to take into account this deformation, the Coulomb effects, all this stuff. The only ingredient that was taken without making so much efforts was the trend of the astrophysical factor, for which we assumed a simple exponential fit of the astrophysical factor in the literature, the one that I've shown you before. So what you can see is this Q parameter that is something that's linked to the momentum distribution. So that let's say the momentum of the spectator particle that you remember from my previous slides. Instead of having this bell-shaped stuff, you have something more complicated, and especially you see it's zero when you at zero, let's say. That is the opposite you usually have when you have distortion measurement. So doing all the calculation, we got a very good result, except at the high momenta. The interesting point is that this high momenta, this high value of Q, correspond to low relative energies in your oxygen-oxygen fusion. So it means that our parameterization, that is just this simple expression fit, probably is failing. And of course, this is telling you that there is something that is not working in your plots. But the good point is that it means that there is some physics behind, because probably there is something that is not working with the astrophysical factor that it's presently available in the literature. And you have to make something different. But of course, statistics is not enough to tell and extract a significant astrophysical factor so far. So we have only some hints that is some physics behind it that's very interesting to keep doing the measurements. So please give us money for the measurements. So, okay, just joking. Okay, so this is essentially what I wanted to tell you. So it seems that it was faster than I expected. And this is my summary. So essentially, I've told you more or less why indirect methods can be useful, like complementary to direct measurements to get to astrophysical energies. And this is just some cases that I've shown you, but in some cases, like for instance, where you have radioactive nuclei and you have neutron-induced reactions, in those cases, indirect techniques are the only approaches that can get you a cross section. Okay, so this is just one of the examples, but you can think about many applications, some of them that are unique to indirect methods. And I've shown you 3 results in increasing order of difficulty, I would say. So the aluminum-27 p-alpha reaction, carbon-carbon fusion, and the last result that is still under evaluation is oxygen-oxygen fusion reaction. So, and I hope I convinced you that it's very useful to carry out these indirect measurements to get the statistical factor at low energies, and all these efforts can get you, some improvement in our present day understanding of these cross sections. It's okay. Thank you for your attention.
Great, thank you. Question?
And thanks for the very nice talk, but I want to be practice. Let's talk in terms of years. In 5 years from now, we have something about the oxygen 16, and especially the ratio between the 2 exits, plus the phosphorus 31 p-alpha, just to have the amount of protons and alpha you have. So let's be practice. 5 years.
So right now, what we have is that we have data, but we don't have people. So we have the situation right now, it's like this. So we have a lot of data. I mean, statistics is still not very good, but we can think about, for instance, relaxing a little bit our constraints, because usually we select only a bunch of data that we feel that's the best ones, but you can release a little bit these constraints and improve a little bit the statistics, for instance. So we could have some data, but then now the problem is that the people that are supposed to work on this are not working on this because they are involved in other stuff. And so it's, I think, I hope that in 5 years we can get something, because in principle we have, but I'm a bit pessimistic about that. Let's hope and get, I mean, maybe in this talk, people like it and want to participate in this business. Let's see. It was very painful to get the theoretical model. So it took many years to develop a theory for that. So now that we have the theory and we have the data, maybe we could get the results. That would be very good, but it's just a hope at present.
Why did you choose the number 20 and not oxygen 17 or whatever is above 16?
I would say a posteriori could have been a good choice, but at that time we thought that this was easier indeed, and it was not. One of the because there are some other constraints, like you have to have some clusterization, okay? So you want to have that your system can be described like oxygen 16 plus alpha, and this was the case for neon, more or less. But yeah, but then you have to take into account what is the wave between the two. So is this S wave or P wave, the relative motion? Because this is introducing additional complication in the theory, okay? So usually what we do is that we want to have S wave between the clusters inside the Trojan horse nucleus. But in those cases, that was not the case. So like, for instance, carbon 13, okay? If you want to measure carbon-carbon fusion using carbon 13, in that case, we didn't use it. We went to nitrogen 14 because of this wave, relative motion. So usually the choice of the Trojan horse nucleus, it takes some time to understand what is the best, and sometimes we don't get really the best. But you know, we have done all the efforts to get the theory, and the theory looks like it's working. So maybe it's not the best, but at least it's working. Of course, one thing that we have done in the past, and it's always useful to do, is to test different Trojan horse nuclei. For instance, we did some tests using deuteron and helium-3, or like lithium-6 and helium-3. And usually, you know, this is telling you what is also your systematic uncertainty. So probably also in these cases, when you get a result from neon 20, it's useful to check a cross-check with using another system and do the measurement again, you know, just to make sure that you don't have any systematic uncertainty. So yes, so probably neon 20 is not the end of the story. We need to go to some other system and check if your model calculation is working. So this is some additional work you need to do. There are two data sets, one at low energies and one at higher energies. So that one was for normalization and check, and the other one was to get the data at astrophysical energies. So far, we just stopped at this high energy data for the cross check, and we need to go to lower energies, but we will see, because it's still the situation is ongoing. We have also a list of systems that can be used to transfer alpha particle. That is, I remember, for instance, well, and so to transfer an oxygen 16 nucleus, that it's also a possibility. But right now, I will say that the manpower is the great problem. We have like the will, but we don't have the hands at present.
Okay. One more question here.
For the carbon 12, do you need to normalize to each reaction channel, or is it once and then all the other calculations follow? Just to explain, I mean, with direct, we typically measure the P1 or the alpha one, and this would be a really another possibility to show how the other channels behave there.
You can do, let's say, all the ways, I would say. So you can choose one channel and normalize just one channel, and then you get the normalization the other channel. You can also do the opposite. You can normalize each channel and check for the compatibility, for instance. This is one of the things we do. For instance, we measured in the past the beryllium 7N, P, and N alpha reactions, because there are two different channels, okay? And in that case, we made the test. So we normalized it for each channel separately and do everything all together, let's say, and we could check for the compatibility. So this is another check to test if the method is working, let's say. So in this case, we did the normalization to just one channel. And then because in only one channel at that time, there were good statistics, so we can reduce the systematic uncertainty coming from the normalization, okay? But if more data are coming and the uncertainty is getting lower, it's worth to make new normalization procedures and check how much we can improve our result, both in terms of uncertainty, but also in terms of the absolute value, because what we get is in arbitrary units, okay? So the absolute value can be a little lower if the data get a little lower. So we just have the trend, but then we have to have very good data, direct data, to have very good normalization and very good absolute values. And then, of course, the more channel we have, the more tests we can do and the more accurate results we can get. hopefully.
If I remember well, there was another carbon-12 plus carbon-12 experiment performed after the paper was published. Is this one analyzed, and did you get the same result than before?
Aurora. She's the expert, so she's telling you more than I can say.
Yeah, I should say that what Marco was saying for oxygen still holds true also for this carbon-carbon data. But I can tell you something because we did a pre-analysis and the problem, okay, the quasi-free mechanism is there. The problem with this data is that we don't have, so we don't see the 4 channels overlapping in the same relative energy region, because indeed the energy we have chosen for our first experiment was the proper one, okay? So going up with the energy, you see the first, so alpha 1 and P1 channel, they are populating a larger energy region, which is not overlapping with the astrophysical region of interest, and we get just the overlap with the ground states. But we have very interesting results because we see other resonances at higher energies that are confirming what is present in the literature. So let's say from the astrophysical point of view, probably will not add anything, but we can add something for the spectroscopy, which is a good result.
Yeah, one more talk, right?
Yeah, we have one.
Okay, thank you.